All right, today we're diving into a really radical new idea that flips one of our most basic assumptions about the universe right on its head. This comes from what's called the postmodern unification theory, and it all kicks off with one simple, mind-bending question about the space between, well, everything.
Seriously, just pause and think about that for a second. We look out into the cosmos, we talk about the void between stars and planets, and we call it empty space. But what if that's completely wrong? What if every single point in the entire universe is already owned, already occupied?
You know, for centuries, we've been on this epic quest, right? Smashing particles together in giant colliders, searching for the absolute smallest, most fundamental piece of reality. We've got our quarks, our leptons, but this theory suggests we might have been missing the most basic building block of all.
So this theory throws a new hat in the ring. And this isn't just another particle to add to the standard model. No, this is something way more fundamental. We're talking about the absolute, indivisible unit that everything else is built from.
And this candidate has a name, the Foundon. The name itself kind of gives it away. It's the foundation. And its defining feature, its whole deal, is unlike anything else in modern physics.
So here it is, the core idea in a nutshell. A Foundon is the absolute fundamental particle. But here's the revolutionary part. Each one has its very own private, exclusive piece of the vacuum. It literally owns its own chunk of space.
And this whole concept is built on two simple, totally unbreakable rules. First, every Foundon has its own private turf, its domain, which the theory calls omega. And second, the amount of vacuum it holds, this quantity they call Q, is constant. It never, ever changes.
The best way to think about it is like this. Imagine at the dawn of time, every Foundon was given its own little plot of land in the universe. Now that plot can stretch and get bigger, or it can shrink and get smaller, but the land itself always belongs to that one Foundon. And here's the kicker. There's no public land. There's no unclaimed territory, anywhere. Okay, so this immediately leads to a pretty fascinating question, right? If there's no unclaimed space, and Foundons can't just overlap their property, how do you get complex stuff? How can you have one particle existing inside another particle's territory?
Well, the theory answers this with this really cool idea of host and guest Foundons. Think of it like a set of cosmic Russian dolls. You can have a gigantic host Foundon that contains countless smaller guest Foundons inside its domain. So for example, all the zillions of Foundons that make up the Earth are guests living inside a much, much larger host Foundon, whose domain is the space our whole solar system occupies.
Okay, so we've got these particles that own space and nest inside each other. But what's actually happening inside one of them? Are they just static, boring blobs?
Oh, not at all. A Foundon is super dynamic. You can picture its internal space as a kind of field where this thing called vacuum intensity can be different from place to place, almost like changes in pressure inside a fluid. And this internal field is always moving, always shifting, constantly trying to find a state of perfect balance or equilibrium.
Now the math behind this gets pretty complicated, but it all boils down to a really simple, intuitive process. Step 1, something disturbs the Foundon's internal balance. Step 2, that disturbance just flows through it, kind of like how heat flows from a hot area to a cold one. And finally, that flow just keeps going until everything is balanced out again. It's just a natural tendency to settle down. And this leads to a really key principle in the theory about energy. If you leave a Foundon alone in a closed system, its total energy can only ever go down or stay the same. It can't just gain energy out of nowhere. It's always fundamentally trying to shed energy and get to a state of minimum effort, basically a state of perfect rest.
So we know they're dynamic on the inside. But what happens when these little plots of land, these Foundons, actually press up against each other? How does that change things?
Well, if a Foundon is just left to its own devices, floating in space, it naturally wants to be a sphere. It's just the most balanced, stable shape. But the second its boundary touches another Foundon's boundary, that's when things get really interesting. The forces between them can push and pull and warp its shape into all sorts of wild configurations.
For instance, if it's getting squeezed really hard from the top and bottom, it might bulge out around the middle and get pinched at the waist, creating this sort of two-lobed, almost peanut-like shape.
Then you've got this. Under just the right conditions, where its center has a lower intensity than its outer edges, it can actually pop into a temporary but stable ring shape. Yep, a torus, a donut.
And check this out.
If it's interacting with a whole bunch of smaller foundons all along its border, it can develop these tiny, repeating, jagged edges, kind of like the teeth on a saw blade. The possibilities for complex shapes are pretty much endless.
All this talk about shape and how these things interact obviously brings up some big questions. So for this last part, let's take these ideas and apply them to the cosmos at large. And let's bust a couple of myths that you might be thinking of right now.
This is the big one, right? The most obvious question. If there's some huge foundation that contains our whole solar system, does that mean the foundation is the solar system?
And the answer is a hard no. Absolutely not. Remember that host and guest thing we talked about? A planet, a star, even an entire galaxy is not a single foundon. It's a massive collection of countless guest foundons, all clustered together inside the domain of one single enormous host foundon.
Okay, second big question. If their borders are all flexible and they're constantly pushing on each other, can they, trade a little bit of their vacuum back and forth?
Again, nope, no way. Remember that second unbreakable rule? A fondant's personal amount of vacuum is constant. Its private property is sacred. It can never be breached. All the action happens at the boundary through forces. It's like two balloons pushing against each other. They can squish and deform, but they never, ever exchange the air inside.
And that all leads us to the final and most profound takeaway from this whole theory. If this idea is right, there's no such thing as empty space. There are no ownerless voids out there. There is just a universe that is completely, totally filled by these fundamental particles, nested inside of each other like infinite Russian dolls, pushing and pulling at their boundaries forever.